All right, so last time we went over exercise 8.2, or we stopped with exercise 8.2. The basic idea is I just want you to look at the code. Part of the idea here is that this folder actually makes a fairly decent code repository. The sort of thing that you might want to replicate, the structure of the code, the way that I create implicitly hidden defs using the underscore, and then I wrap them in a wrapper that's not hidden. All of those things are just stylistic details that you might want to replicate in your code. So I'd like you to look back at the online lronline.py to see that code. Okay. So we won't go over that. And once you do that, you can also get some sense of what the arguments are doing, and then just play with all of them, all of the decay rate in particular, and then the choice of whether you're using the square loss or the absolute value loss to determine which of these you're using. So play with those arguments and see just when you achieve convergence and when you don't for the wine data set. Okay, so for the perceptron, I want you to, okay, so that was, that's the SGD is a method that is applicable pretty much anywhere where you could use empirical risk minimization. If you have a loss, if you have a predictor function that has certain parameters, then you can run this SGD. If you have a non-differentiable loss, so like that absolute value loss that's not differentiable at a point, then you can use the subgradient instead of the gradient. And so what if we just applied this to the support vector machine setting? So if we recall support vector machines, it could be written in the following way. It's our 2 norm squared of our theta is this penalty here times lambda plus this data-driven loss term. So this is the average of the hinge loss. And so we can just think about it as you have your hinge loss is your loss. Right? So let's think about empirical risk minimization with this hinge loss. And then we also have this squared regularizer for support vector machines, and we'll come back to that. I'm also just assuming that the 0th term of x is 1, and the intercept is getting wrapped up in this. Okay, so let's recall this is what the hinge loss is, and so if your yi xi transpose theta is greater than 1, then the sign of this matches the sign of yi, and so you had a correct classification. You still incur some loss until this exceeds 1, and then and this is for yi has to be encoded as -1, 1 for this to be the loss. Okay. So the subdifferential, let's just think of the subdifferential of this loss term, this hinge loss. This is minus yi times x if this is greater than 0, if 1 minus yi times x transpose theta is greater than 0. Right? And so that's when you have when you're on the wrong side of the margin, effectively, when you're either within the margin or on the wrong side of the hyperplane. That's what this is. And so then in the case that this actually exactly matches 0, and this is actually going to happen for some of your these xy pairs, those are what's called the support vectors, are these. Right? And so in that case, you have this non-differentiability of this loss function, it's the hinge loss, and the subdifferential, unsurprisingly, is the entire interval from 0 to minus y times x. Okay, and then it's 0 if 1 is equal to y times x transpose theta. If this is negative, I'm not sure if this would ever happen in this case, but if, yeah, this could be negative, then you would just switch the order of these intervals. So it's whatever numbers are between 0 and minus y times x. And actually, I'm abusing notation a little bit here. This interval, because this is a vector, This is a vector. All of these are vectors, right? So when I write in interval form, the interval between 0 and a vector, I mean you take every component and think of the interval between 0 and that component. And then you have to do a Cartesian product of those intervals. So that's a very technical detail, but this actually does matter. So I'm being a little loose with my notation here. And then it's exactly 0 if you're on the correct side of the margin, because then the loss is just 0 exactly. And in this interval, we're just going to choose the subgradient to be 0 whenever we can. So this is a subdifferential. The subgradient being 0. If this happens, we'll just set the subgradient to 0. So we don't have to really think about this subdifferential too deeply anyway. So for the perceptron, our subgradient of this loss is equal to this loss. We're going to write it in this form. Actually, so this is kind of interesting. I wrap the regularizer term into the loss. And this is fine because when I average these over all of the training points, if I average these over all the training points, well, the average of this gradient, of this 2 norm, over all the training points is just the 2 norm because it's a constant in the index. It doesn't depend on x or y. And so if you look at it, this you could write as the average of just these individual terms. So I've been a little, I was a little coy with this and on purpose. This could be written as the average of all of these components, or equivalently, it could be just the average of this component plus this component. It's the same thing. So we're going to think of our loss as just this entire thing. So let's think about it. This is our subgradient. If we use that subgradient that I mentioned before, where we select 0 whenever we can, this is minus y times x plus the plus lambda times theta. Right? And this happens if you're on the correct side of the margin. Otherwise, it's 0. Right? So it's 0 whenever it can for the hinge loss. For this part, this still has a non-trivial subgradient. And so in the case that we are on the correct side of the margin, we have minus y times x plus lambda times theta. And then otherwise, it's just lambda times theta. And so our STD in this case is going to make the following update. Theta gets 1 minus lambda times eta times theta. Right? Plus, then you have this term, which, let's think about it. Right? So this is just a yt, xt indicator of this. Right? So this is just the yx part is here. Right? And this lambda theta is this part here. Right? We're always removing some lambda theta times eta from theta. So let's think about this part here. So if we're on the wrong side of the margin, right, for SVMs, let's remember this. If we're on the wrong side of the margin, then we also add in this part, which is eta times yt times xt. Right? So if we were on the wrong side of the margin, then we were either incorrect or we were correct in our prediction, but it's still not as correct as we would want. It's not so correct that it would get us on the correct side of the margin. So let's just think of this as incorrect, right? If we were incorrect, then, sorry, this should be ytxt. This is incorrect, then we're going to add to theta eta times yt times xt. Right? And so suppose yt is 1, right? Then if yt is 1, then we're going to add to theta some amount of x. Okay? So if y is 1, we're going to add to theta some amount of x. So we're going to sort of move theta in the direction of x. In the other case, if yt is minus 1, then we're going to move away from the direction of x. Okay? And that's if we were wrong. And the way to think about this is that we're sort of trying to align theta more and more with the x's that are 1, because we're just going to look at x transpose theta to determine whether we're going to predict a 1 or a minus 1. So we want theta to be aligned with the x's where there's 1s and misaligned with the x's where there's minus 1s. Right? And so that's what the STD does intuitively. Right? Now, this isn't quite the perceptron. This is just STD applied to support vector machines. But we can approximate what's known as the perceptron, and we'll outline the perceptron here. So let's just recall that lambda approaching 0, that means that our margin is getting more and more narrow. So we're going to think about the limit as our margin gets more and more narrow. And the reason why we think about this is if lambda is 0, then we're going to allow theta to be very large. And if theta is very large, that means that we have a narrow margin, right? Because the margin width is inversely proportionate to the norm of theta. Okay, so as lambda goes to 0, the margin is going to get more and more narrow. And this is equivalent to reducing this 1 in this thing. So in class, someone had asked me, why do we choose 1? Well, 1 is arbitrary. All of the logic of the support vector machines would work out if we set this 1 to be alpha, for example. And really what we're saying is that our margin in this case, it gets wider if that alpha here, whatever this 1, if we increase that, right? And it's getting smaller if we decrease it. So let's think about decreasing this 1, making this 1 be 0.01, 0.001, so on. In this limit, and we set that eta equal to 1, the learning rate equal to 1, then this update becomes the following thing, because this is when y times x transpose theta is less than or equal to 1, now that goes to 0, right? That's what this indicator becomes. Let's think about this. Lambda is going to 0, so this is going to drop out, right? Eta is 1. Eta is 1 here. You have yt, xt indicator of 1 minus y times x transpose theta. Well, this indicator is when y times x transpose theta is less than or equal to 1. Right? We just pull it over on the other side. But that 1, we're also decreasing that, sending that to 0. And so in the limit, as lambda gets really small, we can think that this is actually approximately what the STD update is going to do for SVMs. And this is what's known as Rosenblatt's perceptron. Now, for the update for this intercept term is actually simpler. So the intercept term, this is when there's an x not xt0. It's the 0th component is just 1, and so we just plug in a 1 here. And so the intercept term is going to be simpler. So I'm sort of wrapping the intercept into both the x and making this theta be p plus 1 dimensional, as usual. It's my trick. But if we separately think about the 0th component of theta, this is what it ends up being. So what is this doing in just logically? What does this do logically? Well, first of all, this indicator, this event happens if we were wrong. If y did not match the sign of x transpose theta, then this is going to be negative, and we were wrong, right? Or if it just happens to be exactly 0. So this is what happens if our prediction is incorrect. And so what we do is we take theta and we add to it yt times xt. So if we were wrong, then we're going to and if yt is positive, then we're going to move theta in the direction of the positives. We're going to move it away from the negatives. And there's no additional tuning parameters here. There's no eta and there's no lambda. Lambda is 0 now. And so this is a simplified version of SVM's stochastic gradient descent in this case. And it's the Rosenblatt's perceptron. And so the update for the intercept is even simpler than this. The intercept is just this. And so if we think about this, we're just going to move it, we're going to increase it for the ones that we were wrong about and decrease the intercept for the negatives that we were wrong about. And that makes sense. And so I created a class in the perceptron.py. So I'll ask you to look at this in a second. But it's just it creates this Rosenblatt's perceptron. It's an online learner, so it's designed to feed in one data point at a time, and it just does this. And so you could add this eta parameter if you like. I said that it was set equal to 1, but you could add it in. And then it has a predict and an update beta method. Right? So it updates the beta and the beta 0 and calls predict, just like before. So so in the file, I create the object, and then I also create data, I create simulation data, and I append the losses to it. So this is just the basic structure. This is just a snippet of code from the file. I didn't actually run this because I haven't defined X and Y that would fit with the Perceptron. But you can go and look at Perceptron.py, see how the simulation works. You can get a pretty good understanding of what I did. So we're just going to append the losses for the Perceptron. I'm also going to plot, and so I plot offline, the negatives and the positives here, and our separating hyperplane. So the separating hyperplane are just the points where X transpose theta is 0. Remember that. So the separating hyperplane is kind of reasonable. This is after just a few iterations, and then, so the negatives would be everything classified here. This is miscorrectly classified. These are miscorrectly classified down here. You can imagine once I see these more points like this, if I see more and more points like this, then I'm going to start to shift my Perceptron to look a little more straight up and down. So as we see more points, it's actually a little bit unstable at times, the Perceptron. But as we see more and more points, we get that the Perceptron starts to align more and more with a good decision boundary here. And this is after however many this is, data points this is the decision boundary that was learned. So we continually are updating this. And remember, this decision boundary is a hyperplane that's determined by the thetas and its intercept. And here's after so many points. Okay, so as an exercise, I want you to go and see what I did. So look at Perceptron.py, go through each line in the main code section after the underscore name dunder is equal to main. So that's the thing that gets run if you run Perceptron.py. You could run it if you want, but just look at it, look and see what the helper functions are doing. There's a simulator in there. There should be. There's the class. And just try to get a good understanding of what is happening in that Python file. And just, it's not, there's not a whole lot of documentation in the Python file, but it's pretty well organized. There's minor doc strings and so on. So just look at the way that I organize my code. It might be a pretty good example for you.